All right, this is chapter 4 and 5 review to prepare for quiz 3. So here's some things that you're going to want to be able to do. Find leading term, leading coefficient, and degree of polynomials. I don't want to take the time to remind myself what section all of these pieces are from. So as an example, I could have a function that looks like this, and I want to know the leading term. Well, I don't want to have to multiply it all out, but if I thought about multiplying it out, I'd have an x squared times an x cubed times an x, which would be an x to the 6th, times a 3 plus other terms. And that's my leading term. There's my leading coefficient, and the largest power I get by adding the 2 plus 3 plus the 1. Leading coefficient is just that number. And the degree is 6, which is the power on the leading term. And I can get that by looking at the powers on each of the factors and adding them up. 2 plus 3 plus 1 equals 6. All right, you need to find end behavior, which comes from the leading term. I don't worry about these other terms. That only determines my interior behavior. My end behavior comes from this. It's an even degree polynomial with positive leading coefficient. So it's going to look like this on both ends. It goes to positive infinity as x goes to positive infinity, and goes to positive infinity as x goes to negative infinity. Right? You might want to, along the lines of polynomials, you might want to be able to find a formula from a graph plus a piece of information, in particular point. So if I have a function that looks like this, where that is -3, that is -1, that is 2, and that is 4. And let's say I happen to know that this point right there is 0, -1. I'm just making this up, so we'll see how easy or hard it ends up being. So the first thing I want to do is identify my zeros, which I have, and turn those into factors. So x plus 3, x plus 1, x minus 2, x minus 4. Then I want to find multiplicities. That cuts through, so it has a 1. That bounces off, so let's say it's a 2. That bounces off, let's say it's a 2, and that cuts through, let's say it's a 1. And it's got some leading coefficient. I don't know what it is, but based on the end behavior, I know A is positive. So I'm missing one piece of information, and this is the key that I want you to remember. This is almost certainly not the formula. It has a leading coefficient, and that's probably not going to be the number 1, but you should be able to tell if it's going to be positive or if it's going to be negative. So if A is positive, and I say that's my function, and I know that if I put 0 in, I should get -1 out. I can put all this together and multiply it. A times 3 times 1 times 4 times -4. That's a 4 because I'm squaring it. Which looks to me like -48 equals -1. So A is 1 over 48, and yep, that's positive, just like I thought it would be. So my equation should be 1 over 48 times x plus 3 times x plus 1 squared times x minus 2 squared times x minus 4. That's a lot about polynomials. Let's keep going. What other polynomials could we be curious about? We spent a fair amount of time on quadratic functions. I'm going to go to the workbook. That's what I'm doing right now to find the quadratic function I want to use, because it makes it simpler for me. It's one we've used a lot, so I know it's not going to be on the quiz, which is f of x written in 3 different ways: minus 2x squared plus 12x plus 14. Also minus 2 times x minus 7 times x plus 1. Also minus 2 times x minus 3 quantity squared plus 32. And with this, we can figure out a lot of different information. We can find a max or a min. That's right there. And because my leading coefficient is negative, that's actually going to be a max because it's got to open down. And we can know when it happens. Max occurs at x equals 3. There. We can say, when is this function 0? F of x equals 0 when x equals 7 and x equals -1. We get that from here and here. And we can find out f of 0 really easy. The y-intercept is 14, which we get from here. We can figure out a lot of information from the different pieces or the different ways to represent a quadratic function. So this question might be a good one to review. This is on page 114. All right. In general, we might want to know x-intercepts and y-intercepts. So that's something that's worth figuring out. So if I have a function g of x equals the 4th root of 7x plus 2, I can find the y-intercept, which is g of 0, which is the 4th root of 7 times 0 plus 2, which is just the 4th root of 2. Let's leave it like that. So the coordinate point is 0, 4, 0, 4th root of 2, not 4 square roots of 2. And I can find out when my function is 0, so the x-intercept, by setting it equal to 0. The 4th root, I just raise both sides to the 4th to get rid of that. And I get 7x plus 2, and 0 to the 4th is still 0. So subtract 2, and then divide by 7, and I get x equals minus 2/7. You still see that? My coordinate point is minus 2/7, 0. I'm finding x and y intercepts. All right. You might also be curious about the domain. Well, since it's a 4th root of terms, you have to have those terms be greater than or equal to 0 in order to take a fourth root. So 7x plus 2 has to be greater than or equal to 0. We solve this just like we did up here, and we see x has to be greater than or equal to -2/7. And so then my domain, it can get at that point, because that makes this 0, and then it can go out towards infinity. That's a lot about polynomials, a little bit about x-intercepts and y-intercepts. It's always nice to know some things about rational functions. Like the 4 key pieces of information for a rational function are the zeros, the vertical asymptotes, horizontal asymptotes, and the y-intercept, maybe, depending on what form we have. So if I have a function f of x equals x minus 3 squared over x or times x plus 2, all divided by x minus 7, x minus 4 squared, and x plus 3. I can figure out a lot of information from this. I can find the zeros are when the numerator is 0, so x equals 3 and x equals -2. I can find the vertical asymptotes, which is when the denominator is 0, so that's x equals 7, x equals 4, and x equals -3. Horizontal asymptote, a couple of ways to do this. You could think about if you multiplied all this out, what would the leading terms look like? Or you could say, I have degree 3, 2 plus 1 is 3, over degree 4. So the degree in the denominator is bigger. So my horizontal asymptote is y equals 0. Right? That denominator grows so big, it's going to shrink everything down to 0. And for the y-intercept, I'm just going to plug 0 in for x. I get 0 minus 3 squared times 0 plus 2 over 0 minus 7 times 0 minus 4 squared times 0 plus 3. So that's 9 times 2, that's 18. 7 times 16 times 3 is a big number that I don't want to figure out. So my y-intercept is 0, 18 over 7 times 16 times 3, whatever the, well, that's 48, 7 times 48. So that's something we might want to know about rational functions, and we might want to be able to do that from a graph as well. Let's see, so let's just do this. Let's say that's -4. Give ourselves a horizontal asymptote at -2. Let's call that -2. Let's call that 1. Let's call that 3. Okay. And as I'm drawing this, I'm not sure that it's even possible to have this behavior. Yep, it's possible. I have 2 zeros. Okay. So again, we're just going to identify our information. We're going to find the zeros, the vertical asymptotes, the horizontal asymptotes, and the y-intercept if we can. So the zeros are where my function crosses, x equals -4, x equals 3. The vertical asymptotes, oh, not 3, that should be a 1. Vertical asymptotes are x equals -2 and x equals 3. Horizontal asymptote is y equals -2. Now I can put this information together. As I put my zeros in the top, x plus 4 times x minus 1 divided by x plus 2 times x minus 3. cuts through, so that all makes sense, and it should end up at -2. So I have the same, I have degree 2 in the top, degree 2 in the bottom. So that all makes sense as long as I stick a -2 in front, and that will get me ending up at y equals -2. And this graph is not showing me my y-intercept, but that's okay. This is not something that we always need for rational functions. So that's a bit of a review on rational functions. Let's jump into logs. And exponentials. We'll start with an exponential. F of x equals 5 times 3 to the x. I just want to identify the different pieces of it. This is the y-intercept. This is the base, i.e. the exponential rate of change. And so we should be able to come up with a formula for an exponential function if we're given at least 2 points. 2 is all it should take. So let's say that I'm going to write down a bunch of different points just to keep it simple. 7 times 49, 343, 2, 686. Okay. All right, so we're going to find this formula in a bunch of different ways. The easiest way is if they go ahead and give you the y-intercept, that means that's your coefficient right there, y-intercept. And then how does it change? It multiplies by 7, so it must be 2 times 7 to the x. That's the easiest way to do it. But maybe they don't give you this number. How can you do it? Well, you could say x1, y1 is 1 comma 14, x2, y2 is 2 comma 98. And we want to know the exponential rate of change, which is what number is it multiplied by. So I take 98 over 14, which is 7, right? So the ratio of the y values is the exponential rate of change, i.e. the base. So I know my formula is something times 7 to the x. And now I just work my way backwards. So I knew that I had 1 comma 14. So if this goes down to 0, this should be divided by 7, which is 2. And I get that same 2 times 7 to the x. And the last possibility is, what if they give you numbers that are far apart? So you have something like 3. If I know these points, 1 comma 14 and 3 comma 686, I can still do that division. And that's going to be my base raised to the number of steps. So there's 1, 2 steps there, so it's squared. As a 680, so I take the square root of 686 over 14, and you're just going to have to trust me that that's 7. So I know y is something times 7 to the x. And then I can use the same process to figure out that should be a 2. So remember, if your numbers, if your coordinate points aren't right next to each other, you just find the number of steps between points, call that, I don't know, r, and then you have y2 over y1 equals b to the r. So b is y2 over y1 in the rth root, or raised to 1 over r. And that's how you find an exponential function from some data. growth versus decay. Okay, if I have an exponential function, a times b to the x, if b is greater than 1, it's growth. If b is between 0 and 1, it's decay. And we can't have b equal to 0 or less than 0. So if I give you a funny weird looking base like this, just plug this into your calculator. 0.75 to the minus 8 is approximately 9.998, which is bigger than 1, so it's growth. That's all you have to do. Don't think too hard about all of these numbers you're seeing. Just plug exactly what you see into your calculator. If it's bigger than 1, it's growth. If it's between 0 and 1, it's decay. And that's good enough. That's more than good enough. All right, that's pretty much what we cover with exponentials. You do want to be able to know what your basic exponential function looks like, because it's one of our parent functions. This is growth. And this is decay. And that's all I can think of for exponential functions right now. Move into logs. You will get the full set of, I'm going to use natural log because it's faster to write than anything else. You will be given this information. Now I better use a different one. Log base 3 of 3 equals 1. Base 3 1 equals 0. If log of x equals log of y, then x equals y. You will be given this information. That could be any number. That could be like log base b of b, log base b of 1. You will be given this information. You just have to be able to use it. So if you see a question like log of x plus log of y minus 2 log of z, and you want to combine, you need to look at these different pieces and say, okay, that's log of xy minus log of z squared, which is log of xy over z squared. Or if I give you log of x squared plus 1 times z minus 2 over y cubed times w times u, you should be able to write that as separate logs. The things in the numerator are positive. The things in the denominator are negative. Log of y cubed minus log of w minus log of u. And then look a little bit farther and say, oh, that's something to a power. But if I have an x squared plus 1, logs can't split addition or subtraction. So those stay as they are. It should be 1. And then that, I can pull that power out because the y is by itself. And it looks like this. So you should be able to do that. We're not really getting to using logs and exponentials back and forth. Remember, log is the inverse of the exponential. but we're not really doing that. But I do think it's worth remembering if I say log base 3 of 81 equals 4, what I'm saying is that 4 is the power that goes on 3 to get 81, which now I can write as 4 is a power that goes on 3 to get 81. So it's good to be able to go back and forth between those two different forms of the same mathematical statement. And that's all that I can think of as far as preparing for this quiz in a review of chapters 4 and 5. End of video.